We're going to go ahead and put this, a copy of this PowerPoint in the chat right quick while I'm waiting on this iPad to act right. Give me 1 second. Let me find it real quick. One second. Let me grab it from Gmail. All right. So I just uploaded the document that I'll be using right now, and we're gonna go ahead and jump right in. And today, again, I said we were going to be talking about mass spec. So that's where we're going to start with our lectures on spectroscopy. And yeah, so we talked about the other day about the different ways to characterize compounds. We talked about NMR, we talked about infrared, and I mentioned mass spec. So we're going to talk about that. Like, and what is mass spec? What is it used for, and how does it work? Again, this is probably out of all of the methods, this one is probably the easiest to understand because it's very simple. Every molecule has a molecular weight, and if you inject that molecule into a mass spectrometer, you're going to see a peak for the molecular weight, and then several other peaks that are going to correspond to different fragments. So we'll talk about that. Let me just go past here, right? We already went over this. Infrared tells you about functional groups. UV tells you about pi systems, which I didn't mention on Monday. Mass spec tells you about size and molecular weight. And then NMR tells you the carbon-hydrogen framework. And there are different nuclei that you can study: proton, carbon, fluorine, deuterium, phosphorus, lots of different nuclei that you can study. But we're gonna focus today on mass spec, right? So this is what an actual mass spectrometer looks like. We have a time of flight mass spec here in Armstrong. I think we've had it since 2015. But this is the instrumentation. It's very bulky. They make them now. They have miniaturized mass spec. And every time I teach this lecture, I talk about when I went to a conference in Virginia. I'll never forget this, where we were discussing how to miniaturize mass spec. And now miniaturized mass spec is actually a thing. And then you have portable mass spectrometers that you've probably seen this in the airport when they swab. Well, they don't do it as much anymore, but they used to, after 9/11, swab your bag and then take the swab and put it into an instrument. That was a type of mass spectrometer. What they're looking for are specific compounds, explosive compounds that have certain molecular weights that fall into a certain range of molecular weight. So that is an example of portable mass spectrometers. And I can remember also when my late wife was deployed to Iraq, And you would see on the news every day, you see guys walking around with, this was in 2008, you see guys walking around with these handheld devices, and what they were checking for were chemical weapons, right? Or whether or not a chemical weapon had actually been used. And again, if they know what they're looking for, they know that they're looking for anthrax, or they're looking for mustard gas, or some other um, type of chemical weapon. That chemical is going to have a specific molecular weight that can be detected by a mass spectrometer. So that's what mass spec is used for, to tell us about size and molecular weight, right? And then one of the, or a few of the uses of mass spec, right? You use it to identify unknowns, which is that's often the case. You have an unknown, especially when you use it for like crime scene investigation, and you're looking for clues as to whether or not, maybe somebody was poisoned, or maybe somebody was had overdosed or something like that. Mass spec can tell you if a particular drug is in the system, that drug has a known structure and a known molecular weight. Uh, so you can use it for crime scene investigation, explosives detection. We already talked about that. But known compounds, I showed you the other day. I think it was this class where I showed you that supporting information. I did. It was this class. I showed you the supporting information from that journal article. Well, one of the things that's required to publish any organic research, especially if you synthetic organic, especially if you made something and you've had to prove it, is to quantify that compound by mass spec, right? If you made a certain molecule, it's going to have a molecular weight, and if whatever that molecular weight is, you need to verify it using mass spec. You can also use it to detect contaminants, toxins, all types of stuff. Like I always say this when I teach this part of the class. When you have when you watch like CSI or NCSI, or all these other shows, these forensic shows, Forensic Files on what is it, HLN Network, all those shows, they always have a segment where they show a lab, like a crime lab, and they show a person kind of hunched over an instrument using a syringe to inject in some sample into that instrument. More than likely, that instrument is a mass spectrometer. Now there are a lot of different types. There's some of them have a gas carrier, some of them have a liquid carrier, so it just depends. But there are a lot of different types of mass spectrometers. But the main use is to determine the molecular weight of a compound, right? Even if you know it, you still have to confirm it. All right, so let me show you what the setup looks like. It's a very basic setup where I'm oversimplifying it here because all this stuff is very complicated instrumentation. But your sample goes into what's called an ion source. And then I'm going to show you how this works too. What happens when the sample hits the ion source is it gets bombarded by an electron beam and basically shattered into pieces. Right, that's literally what happens. The sample goes in, it gets busted up into pieces, and then every piece has a mass. And so the pieces go through the mass analyzer that detects the mass of each fragment, in addition to detecting the mass of the original compound before it got fragmented. And then once it goes through the mass analyzer, those pieces are detected, and then it goes into data analysis where you can get a spectrum from that. So how this really works, and this is a PDF of a PowerPoint. So the electron beam is here. Hold on one second. So this is my electron beam. right? So the electron beam is what's going to bombard your sample, right? So you just keep banging on it. The electron beam is basically like a hammer. It's a stream of electrons that you irradiate your sample with. That's the first thing that happens. So you basically, it will be the equivalent of taking a porcelain dinner plate and pounding on it with a hammer, right? Because eventually you're going to hit that plate and it's going to shatter into a bunch of different pieces, and all the pieces are going to have a mass. So that's exactly what's happening here. So you bombard this sample with electrons. You actually lose an electron. That's what this little ball is here. In the PowerPoint, I showed it ejecting out, but you lose an electron. So that's the next step. You eject an electron. When you do that, you generate what's called a radical cation, which is this species right here. Right? That is what gets fragmented, not the original compound, but the radical cation. It gets broken into pieces. In this case, it's a CH4, and I'm gonna actually write this out. So that's a carbon here with 4 hydrogens attached to it. And when you get to the radical cation, which is here, right? That's why we call it a radical cation. It's less 1 electron, so it becomes a radical, and the charge goes to +1, right? This can break apart because that electron beam is still pulsing, beating this thing to death, right? So let's just say, for the sake of the discussion, this hydrogen right here is what's breaking off, right? So we're going to break that CH bond. That's how we get to here, where you have a CH3 radical and a proton as your cation. So once the radical cation, let me put this in brackets. Once the radical cation gets fragmented, whatever 2 pieces you get, one of them becomes the radical and one becomes the cation. So one fragment becomes the radical. I'll fix this before I post it. And then one becomes the cation. Right? That's what happens. That's the essence of it. So you take a molecule, and there are specific fragmentation patterns, which we're going to talk about. It's not just random fragmentation. Depending on the structure of the molecule, that's going to determine how that molecule fragments. So once you get to the radical cation stage, which is immediately, because once you put your sample in, it's going to get hit and it's going to eject an electron and become that radical cation. That's what gets broken apart. So that is going to fragment into 2 pieces, right? Really multiple pieces. If depending on how big the molecule is, it can fragment at different sites, and you'll have multiple fragments. But for here, once it fragments, 1 piece becomes the radical, 1 piece becomes the cation, and that's based on stability, which one is the most stable. In this case, the methyl radical would be more stable than a hydrogen radical, so that's why the radical is here. All right, so you get to determine which piece is the radical, which piece is the cation. All right, any questions so far?
No, sir.
All right. So, Asia, have you heard this lecture before? When you were in FNS, in one of your FNS classes? Did I do this? Because I always do this.
Yeah, I do remember you doing a presentation on mass spec when I was an undergrad.
Yeah. Okay. Yeah. When I think I skipped this year. I owe them an apology because I totally forgot. I had just too much stuff going on. But yeah. So when we think about this, how do we read this, right? How do we know what we have? Well, again, you have a detector and a data analyzer, right? So that data analyzer, excuse me, is going to give you a spectrum to read, right? And this is what a typical mass spectrum looks like. On the x-axis, that's mass over charge. Right, the charge is normally 1 + 1, so it's really just indicative of the mass. Right, that's the x-axis. On the y-axis is relative abundance. Right, that just tells you how much of each fragment is present. Right, and there's some really important peaks in here that we're going to point out. Obviously, I have this one labeled as the base peak. That's your tallest peak, right? And usually the most stable fragment. So the base peak is the tallest peak in the spectrum and the most stable fragment. That's why it's the most intense, so the tallest, right? Because it's the fragment that's most persistent and the most stable. So that's why you see that. You also have what's called the parent peak. Sometimes it's called the molecular ion peak. That's down here. I think for this one, it is 46. The parent peak is just whatever the molecular weight is. Right? That's whatever if the compound weighs 50 grams per mole, then the parent peak is going to be at 50. If it weighs 46 grams per mole, then the parent peak is going to be at 46. If it weighs 100 grams per mole, it's going to be at 100. That all the parent peak is the molecular weight of your compound. There's another peak in here that we have to think about, and that's down here. This is a very important peak. This is, sorry about that, what we call the M + 1 peak. Right? It's the molecular weight of the parent plus 1. It corresponds to the isotope, and what we call the isotope peak. Right? So the natural, based on the natural abundance of the carbon-13 isotope, because we know carbon's molecular weight is 12, the isotope has 1 extra neutron in the nucleus, so the molecular weight goes up to 13. Based on the natural abundance, that's going to determine how intense that actual peak is. Right, so the M + 1 peak is very important. Every mass spec is going to have these 3 peaks at a minimum: the parent, the base, and M + 1. Right, the M + 1 is exactly what it says. It's the mass plus 1. So if the parent is 46, then the M + 1 by default has to be 47. If the parent was 100, the M + 1 would be 101. If the parent was 50, the M + 1 peak would be 51. But if you notice, it's a very tiny peak, and that's because of the natural abundance of that isotope. It's not very high, right? So that's why the intensity on the M + 1 peak is really low, but it is there. All right. Any questions about the spectrum? So you definitely are going to see the base peak, you're going to see the parent peak, and you're going to see the M + 1 peak, which is basically the parent plus 1. Every mass spec is going to have that, in addition to the whatever fragments are present. All right. Questions? Any questions?
I don't have a question, but I do have like a comment, I guess. When I was at Penn State for my Penn State for my internship, they had this machine, and it was kind of like this, but it was like for scents, like for smells.
Oh, really?
You know what that is? I can't remember the name of the machine, but it'll break down a compound like an item or whatever, and it'll like point out the different notes as they occur. If that makes sense.
No, that makes sense. I'm not sure. I'll have to look that up. I'm not familiar with that instrument.
Yeah, it was pretty cool.
In a food lab, like a food science lab?
Yeah, it was a sensory science lab I was in, and she was just showing us the machine. Like, she was saying how it had coffee notes at this time, and later on you could smell something else differently. It was pretty, I just like You heard about that?
It was probably some type of liquid chromatography. Because again, the scents are actually chemicals. And if it's based on the time that you see them on the spectrum, there's probably some type of liquid chromatography, because the retention time is going to be different for different chemicals based on the functional groups that are present. That's pretty cool though.
Yeah, it was.
I'm gonna look that up. Yeah, thanks for sharing that. All right, let's see if we can put this into practice. All right, so we got 5 compounds. I'm gonna put a insert a page right here so we can work through this example. We got, this is my mass spectrum. We have 5 compounds. One of these compounds is going to be a match for the spectrum, or the spectrum is a match for one of the compounds, but one isn't. Right. The other 4 are not. So what's the first thing you would do? I'm just asking this just to see where your mind is right now. What's the first thing you would do if you have 5 compounds and you're doing a mass spec analysis of each of the compounds? What's the first thing you would want to already know before you do that?
The mass, like the weight of it,
Yeah,
atomic mass.
you need to know what the molecular weights of each compound are, right? Before you go and start injecting stuff. So let's look them up. Let's take formic acid. Somebody look that up. And we're just gonna look up the molecular weight of each one. Ethanol, methanol, and isopropanol. You can just Google it. Google somebody, we got 16 people. I know that's 5 people with their phones out. Some of you are on your phone for class. So just minimize Zoom and Google one of these compounds. I'll Google methanol.
Sir Papa just said it, but the formic acid is 46.03 grams per mole.
46.03.
Yeah.
Grams per mole.
For ethanol, I got 46.07.
Okay. Anybody got one propanol? One propanol and isopropanol are probably going to have the same molecular weight. We're going to draw them out too, so we can see them. But isopropanol and one propanol are isomers of one another, so they're going to have the same molecular weight. So if you get one, we can use that for the other one. Anybody got that? One propanol?
Naya put it in the chat. She said it's 60.0952.
60.09.
Yeah, that works. And then isopropyl alcohol is 60.1.
Yeah. So they're the same. They're just isomers of one another. I'll show you when I draw it out. All right. What about, I said I was doing methanol, didn't I? That's 15 and 17 is 32. Right? So we know that these are molecular weights. Now we look at each one of these. So this is methanol. And this is one propanol. This is isopropanol. And this is formic acid. And what else? Methanol, right? And then ethanol is here. It's CH3, CH2OH. Right? So methanol we said was 32. These two were 60.09. And then this was 46. All right. So let's look back at the spectrum itself. All right, you can see the spectrum goes from 10 grams per mole down to 50 grams per mole. Where would it stop if methanol was the actual compound? Where should it stop?
At the mass.
At the mass. Methanol is 32 grams per mole. There can't be something heavier than that in there if it's just methanol in the sample. So can we rule out methanol as the compound that this spectrum corresponds to? Can we rule that out?
Yeah.
Yeah, we can. Anybody not catch that? If the spectrum is from 0 to 50, if it was for methanol, it should be from 0 to 33 minimum, right? Because 32 is the mass and 33 would be the M+1, the mass +1. But it shouldn't be anything past that because the molecular weight is 32, if that makes sense. Anybody not catch that? All right, what about the next two samples, 60.09? Same spectrum, right?
It's not on there. It only goes to 50.
It only goes
right?
to 50. So it can't be either one of these. Do you see how we can, again, if I'm looking for a specific compound and I know the mass of it and I take the mass spec and if it's 200 grams per mole and the spectrum stops at 150, that compound, it can't be in there. Are you following? If I have a sample and I'm injecting and I'm assuming that this 200 gram per mole compound is there, and then when I take the spectrum of the sample, it stops at 150. That tells me that that compound is not there, right? Because the spectrum has to include the mass of your sample, whatever it may be. So those two are ruled out. Now, what we can't rule out are these two, right? Because you can actually see that there's a peak at 46. There's a peak at 47. There's a peak at 45. 31, we're just gonna look at the main ones, 29 and 15. Those are our fragments, 15, 29, 31, 45, 46, and 47. All right, so how do those fragments occur? All right, so let's look at it. So let's take formic acid, we're gonna break it into pieces, right? So if I take formic acid, which is here, so now we're gonna look at the cleavage pattern. So if I take formic acid, which has a molecular weight of, we said 46.07? Is that right? Or 03?
It was 46.03, I think.
All right. So with formic acid, I can cleave, and keep in mind, when I fragment a molecule, I'm only breaking sigma bonds, right? So let me do this also. So I'm not gonna chop it at the pop bond. I can't do that. But I can fragment it here, right? And that's gonna give me two pieces. It's gonna give me, and keep in mind, I'm fragmenting the radical cation of formic acid. So it's gonna give me H plus as a fragment, and then it's gonna give me, actually, let me not do that as H plus. That's a radical. And it's going to give me this as the cation with the plus charge on carbon. I'm following that. If I break that sigma bond, I'm going to get an H, and I'll get the rest of that functional group, that carboxylic acid functional group. So this is 1 gram per mole. And then over here, this is going to be what? 45 grams per mole. Anybody not following that? Because it has the total up to the mass, which is 4. The fragments have to add up to the mass. And the mass is 46 grams per mole. Right, if I cleave it here, I'm going to get 2 fragments. One is going to look like this. And I'll make that my cation again, because that carbon, that can be stabilized by resonance. And then here. That'll be my radical. This is 17. And then this is 29. Those are my fragments. Those are all, that's everything I can get out of this molecule. If I break this, if I break off this hydrogen, it's still going to give me 45 and 1. So that's a moot point. Even though it probably does happen, we're not going to show it here because it's not going to help us. All right. So let's look at the spectrum. I'm actually going to copy this and stick it down here. All right. Now, when these fragments happen, again, they got to match. Everything has to match. So if we look at the spectrum, do we see a peak at 46? That's the parent, right?
Yeah.
So that's fine. Do we see a peak at 1 or a peak at 45? Meaning you lost a proton. Y'all see that?
Yeah, I see it.
See that? Okay. M+1 is fine because the parent plus 1, right? We also see a peak at 29. Is that right?
Yeah.
And we see a peak at 17, maybe. If this is 15 right here, maybe this little small peak down here is at 17, maybe. Right? But how do we account for that big giant peak at 31? Can we account for it with this molecule if these are all the fragments we can get? If I can't break it up into any other pieces? And even past that, what would I have to subtract from 46 to get 31?
25. Right? No. Oh. I was thinking about it too fast. What's the numbers again? 46 to 29?
No,
To 21?
46 and 31.
Oh, sorry. 15.
15. But I don't have a functional group present that has a mass of 15 in formic acid, do I? I got 17, I got 29, I got 45, and I got 1. So does this structure for formic acid match the spectrum?
No.
It doesn't. I can't account for that peak at 31. All your peaks in the spectrum have to be accounted for. Right, so if I can't account for that, then the spectrum I can't say that this is the spectrum for formic acid. Now let's do the same thing for the other molecule, which is ethanol. All right, so I'm gonna write this out as CH3, CH2, OH. Keep in mind, I can cleave any one of these sigma bonds, right? And I don't break apart the actual molecule. I break apart the radical cation. That's what gets fragmented. So let's just start on the left end, right? If I break this sigma bond, I'm going to get two fragments. I'm going to get a CH3, and I'll make that my radical. And then I'm going to get a CH2OH, and I'm going to make my cation, because the oxygen next to that can stabilize it through resonance. I can push these electrons here and stabilize that. Right, so that's why I made that the cation. A methyl cation is the worst possible cation that you can make. The absolute worst. So it's very unstable. All right, so that's why I made the other side the cation. What's the mass for the CH3 by itself? Carbon is 12, hydrogen is 3. This, again, that's why I said mass spec is the easiest to grasp, because it's just adding and subtracting.
It'd be 17, right? For that one. No.
Three.
Oh, 12. Okay,
Yeah,
okay. I'm
12.
thinking, okay.
Yeah,
Yeah, I was
good.
thinking about carbon as being 14. Sorry.
Yeah, no, it's okay. It's okay. Carbon is 12, even though there is a carbon 14 isotope. It's really rare, but it exists. So what does the other piece have to be if the total has to be 46? Is that right? It should be 31. If I add them together and make 46. Is that right?
Yes.
All right. What if I cleave here? That's going to also give me two fragments. It's going to give me an OH, which I'll make my radical again. And it's going to give me CH3, CH2. Which I'm going to make my cation. It's bad. It's not a great cation. Probably it's actually pretty bad, but I think it's better to put the plus charge there. All right, so what do we have here? OH is 16, H is 1. So there's 17 grams per mole. What about this piece? If the total has to be 46.
You said this one's 46 too?
The molecule, the overall molecule is 46. So any fragments I break off, the total has to be 46 between the two fragments.
It'll be 29.
Yeah, so 29 would be the other piece. And I think you can see now that if I can copy this, if we put that spectrum here, right? If we look at the spectrum, we can see now every peak is accounted for, right? The base peak at 31, we see that right here. Right, we see the peak at 15 here. Right, we see the peak at 29 right here. So all of our peaks are accounted for. And we even have, again, at 17, we had it marked off. It was a tiny peak right here. You can see that as well. right? And then of course, you have your parent here, which is 46, your parent plus your M+1, which is that, which is 47. And then 45 would just be simply the loss of a proton. That can come from anywhere. It can come off a carbon or it can come off an OH group. All right, any question? Ooh, got 2 minutes left. Any questions about that? So again, with mass spec, if you know the molecular weight, if you know the structure, you can basically chop the structure up into pieces. And you can match those pieces up to a spectrum to see if it fits, to see if it matches. All right, any questions about that? I think what we'll do on Friday is to go through the different cleavage patterns. We'll do a couple, an example, and then, well, several examples, and then we'll be done. But this is, you'll see this on that exam over the weekend. So if you have questions, please ask them. All right, we're gonna stop here then. And I'll post this to Blackboard. I'll clean it up a little bit and post it to Blackboard.